Today's program is being recorded. Any views expressed in this webinar are for general educational purposes only and do not represent any official views or positions of the sponsoring or presenters organization. We are looking forward to your questions at the end of the program. Please keep sending them anytime during the talk. And you can use the Q&A section for sending your questions. Greetings and welcome to today's educational program. In the webinar series of Preparing for Process Analysis, this is webinar number 7. Don't be afraid of hypothesis testing by Sandy Furterer and Doug Wood. This is your moderator, Shobha Mittal with ASU Quality Management Division. Today we have the distinct pleasure of hearing from Sandy Furterer and Doug Wood. Please join me in welcoming them. Dr. Sandy Furterer is a professor of practice at The Ohio State University in the Department of Integrated Systems Engineering. She has applied Lean Six Sigma, systems engineering, and engineering management tools in healthcare and other service industries. She previously managed the Enterprise Performance Excellence Center in Healthcare System. Dr. Furterer received her PhD in Industrial Engineering with a specialization in Quality Engineering from the University of Central Florida in 2004. She received her MBA from Xavier University and a bachelor's and master's in science in industrial and systems engineering from the Ohio State University. Dr. Furterer has over 25 years of experience in business processes, quality improvement. She is an ASQ certified Six Sigma Black Belt, certified manager of quality and organizational excellence, certified quality engineer, an ASQ fellow, and a certified Six Sigma Master Belt. Dr. Furterer is an author and co-author of several academic journal articles, conference proceedings, and 9 reference textbooks. She co-edited the ASQ CQIA Handbook and the ASQ CMQ OE Handbook. She is also the editor of the ASQ CQPA Handbook. She has published a textbook on systems engineering called as Holistic Lifecycle Architecture, Modeling and Design with Real-World Application, CRC Press 2021. Welcome, Sandy.
Thank you. Hi, everybody.
Mr. Doug Wood has worked over 40 years in the areas of cost of quality, office waste, root cause analysis, performance measurement. He has helped others with various ASQ certifications in quality auditing, management, and engineering. He has also taught audit, Lean Six Sigma, cost of quality, statistics, and failure modes and effect analysis. He has 4 ASQ certifications, CQE, CQA, SSBB, and CMQOE. Doug was the 2023 recipient of the ASQ Quality Management Division Howard Jones Award given for outstanding long-term services as the Vice Chair of Education from 2015 to 2021. Doug has published 3 books, The Certified Manager of Quality Organizational Excellence Handbook, 5th edition. He co-edited this with Sandy. The Executive Guide to Understanding and Implementing Quality Cost Program, Reduce Operating Expenses and Increase Revenue, Principles of Quality Cost, Financial Measures for Strategic Implementation of Quality Management, 4th edition. His firm, DC Wood Consulting, LLC, has worked with clients in manufacturing, healthcare, and transactional businesses. The company's website is www.dcwoodconsulting.com. And so, without further ado, it is my pleasure to introduce Sandy Furterer and Doug Wood. Sandy and Doug, the floor is all yours.
Thank you, Shobha. Really appreciate that. Nice introduction. Sandy and I flipped a coin, and I'm going to start, and then she's going to finish. We're going to go over these slides. Hopefully, this will bring you up to speed on the keys to hypothesis testing. So we're going to begin here, and we're going to say, so what is it good for? But then we're going to get into some of the weird language, right? What is a null hypothesis? What is an alternative hypothesis? We're going to talk about the usual steps that you go through. We're going to discuss what it means when they talk about a critical region. And then we're going to finish up with what are some of the common pitfalls. We will be providing you with an example, or a couple examples of how this works. So again, on our agenda, definition and uses, what are the main steps, null versus alternative, and what is significance level. We're going to talk about one-tailed and two-tailed tests and how that pertains to the critical region. We'll give you an example, and then we're going to discuss what it means to reject or fail to reject the null hypothesis. That's what hypothesis testing does. And we will also discuss what it means to get a type 1 and a type 2 error. So, to define this, hypothesis tests let us make a definite decision based on observable consequences. They show what the chances are for the two options in a decision. They're used to do many different things. For example, they're used to prove that a goal was met, like achieving 80% customer satisfaction. And in the words of Dr. Deming, how do you know that you accomplished this? It's used to be certain a new process is performing better than an old one. It can answer the question, what is the probability that these results could have occurred by chance alone? And it helps us determine if there's a real difference between two different populations. If we have only a small set of samples, small meaning, less than 30. So the steps in hypothesis testing are to, 1, state the null and alternative hypotheses. We're going to talk about what that looks like. Next, you choose a significance level. See, this is a management choice. How sure do you want to be? And you can say, well, I want to be 99% sure. I want to be 95% sure. 95% is very common in most business. Then you're going to need to decide, is this a one-tail test or a two-tail test? In other words, are you looking for a difference that could go higher or lower? Or are you looking for just, is it higher? That would be a one-tail test. Then you collect and analyze your appropriate data. You choose a formula and you calculate the test statistic. Now, you compare the test statistic you calculated from your data to a table that gives you a critical region. And if it falls in that region, now you can either fail, depending on where it falls, you can either reject it or you can fail to reject the null hypothesis. So it's not that complicated. So the null hypothesis is a statement of no effect or no relation between variables. It represents the default position, suggesting that the observed difference in effect in the data is due to chance or random variation. In other words, it assumes there is no meaningful relationship or no difference between the variables being studied. That's what a null hypothesis says. For example, let's consider a study investigating whether a new drug is effective in treating a particular medical condition. The null hypothesis in this case would state that the drug has no effect on the condition and any observed changes in the patient's conditions are purely coincidental. Okay? Now, the alternative hypothesis, of course, is the opposite. It says there is a specific effect or relationship between the variables, that indeed there is actually a meaningful difference between them. Continuing with this previous example, the alternative hypothesis would state that the new drug has a significant effect on the medical condition. It suggests that any observed changes in the patient's conditions are a result of the drug's effectiveness rather than random choice. Now, the null and alternative hypotheses are mutually exclusive. By that, we mean if one is true, then the other must be false. During hypothesis testing, the goal is to gather evidence from the data, from your collect information, and determine whether there's sufficient support to reject the null hypothesis in favor of the alternative hypothesis. And so when we say reject or fail to reject, we mean the null hypothesis. That's what we're dealing with. Now, we need to choose a significance level. Our decision depends on this. So the red areas here show the size of the p-value. Okay, you probably heard that associated with this. What we're seeing here is the spread, the black line represents the spread of where all of our values might be. Okay. And the p-values help us just tell us how likely is it to see the observed results if the null hypothesis is correct and only chance is operating. To understand the meaning of this, we need to have some kind of a standard. This is our significance level, a fixed significance level, or alpha, in this case, alpha of 0.1 is split in two because we could go either high or low. Okay. So a p-value of 0.1 gets split to 0.05 on either side when it's a two-tailed test. We're going to talk about that again later. For example, if you wanted a 99% surety, then you're going to take 0.01 p-value and you're going to split it to 0.005 on either side. So it's going to be a lot smaller area in red there, okay? So when we find out that we're in the red area, it helps us make our decision. Now let's talk about one-tailed and two-tailed tests. So let's say we're asking, does the average of population 1 exceed population 2, exceed population 1? So here's a histogram, and this is showing us, we're interested in the exceed side, okay? We're not saying, is it different from, we're saying, does it exceed? So this becomes a one-tailed test, okay? We're interested in that side of the histogram. So here's the other population. We're still interested in this side because we're going to compare sample 1 to sample 2. So here's sample 1, here's sample 2. Can you tell? The average is different, apparently, the mean, but we don't know if it absolutely is. Could this be chance? Now, if our question was, does the mean of population 1 differ from population 2? That means it could be on either side. Now we're interested in both halves. This becomes a two-tailed test. Okay. So the question is, are you seeking to evaluate less than, more than, or are you seeking to say, is this the same as or different from? Again, that's another way of saying one-tail test or two-tail tests. So here's our sample 2. So again, sample 1, sample 2. Yeah, this is kind of like going to the eye doctor, isn't it? So because a two-tailed test can fail in two places, then you take your significance level and divide by 2, as I mentioned earlier. So if we were going to do 90% significance, we want to be 90% sure of our decision. So we take 100 minus 90, and that is 10%. We divide that by 2, and that becomes 0.05, and we put that on either side. And this is what we're going to do when we compare it to our critical value in our data set. So this gives us a standard to compare against. If we're doing a one-tail test, that 90% significance becomes just 0.1. You see, all the significance ends up on one side. We're not splitting it in half. Okay? So that just kind of helps you understand what's going on. So it depends on your circumstances. Okay? Do you want to be 99% sure? Do you want to be 90% sure? Do you want to be 95% sure? And are you looking at different from or greater than or less than? Those things all come into that. Okay, now, using the p-value with a t-statistics to make your decision. So the rule is, if P is low, HO must go. In other words, your null hypothesis is not confirmed. So if our calculated p-value from the statistic, the calculation, the formula, using our data, is below the significance level, is smaller than these values, we would reject the null hypothesis and conclude that there is a difference. If the p-value is larger than our significance level, then we fail to reject, and we conclude there's not enough difference to say that the processes are significantly different. That's not quite the same thing as saying that they are the same. Okay, you haven't proved that they're the same, but you cannot say that they are different. Okay. Generally, what that means is we're more confident that chance is operating here. So you can calculate this in Excel. The p-value of the t-statistic uses a function in Excel. Okay, and the way this looks is you put in your values mapped from your spreadsheet, and you tell it your degrees of freedom, and it returns the value, the formula result. Okay, degrees of freedom, that's a new term. So our number of samples minus 1 tells us what our degrees of freedom are. That's another thing you need to add for the statistic to work. All right. So we need to collect appropriate data. All right. We want to observe the usual rules. We've done a video earlier on collecting data effectively. We need to ask ourselves, well, how likely is this data going to show what's going on? We also have to say, we have to be consistent and complete and accurate. We need to make sure that our data is not messed up by how we're collecting it. We want to avoid errors and omissions and aberrations and instability. Now, realizing the real world has plenty of these things, it takes a lot of planning to collect data that does not have these issues. Every now and then you will hear about a scientific study where somebody fudged the numbers. Probably their data collection was off and they really wanted to publish, so they faked it. President of Stanford just resigned recently over a scandal about this. So make sure your measurement tools are calibrated. Uncalibrated measurement tools are going to give you bad data. You want to make sure that those people collecting data do it correctly and consistently. So you have to train them. And in other words, you have to calibrate the people that are collecting the data. All right. You should document your data plan in case you need to repeat it. I'm going to say that again. Document your data plan in case you need to repeat it. Okay. If you are sampling, make sure your sampling is random and representative of what's going on. Now, the next step is to analyze this appropriate data that you've collected, and much of your initial analysis will be taken looking at averages and standard deviations. It's a very simple thing to do in Excel. And remember, the number one rule of statistics: plot your data. Make a picture of it. Does it look odd to you? Okay. The number two rule of statistics: examine your central tendencies and your dispersion. So this will help you see whether the data is doing what's expected. So Sandy, I think you're going to take over here, right?
I am. I'd like to welcome everybody and thanks for joining. This is great. We have a truly international webinar here tonight, and plus my dogs and cats are around. So there we have it. So even dogs and cats are interested in hypothesis testing. Amazing. So I just wanted to start with, before I jump into the example, and thank you, Doug, for giving us the background of statistical hypothesis testing. I just want to ask, so we titled this, don't be afraid or don't be scared of hypothesis testing. So when you might not be now, but when you first started, and I'll tell my story of when I first started the very first course of probability and statistics that I took and why I was scared. But just throw into the chat there, and I'll just read through a few of those of what scares you about hypothesis testing. Okay, null and alternative, never understood that. Okay, talk about that for sure. The time involved, not a lot of data. The beta error, good. We're definitely going to talk about the not enough data. And p-value, we're going to talk about that. This is fantastic. Remembering the acceptance criteria, we will talk about that. We're not really going to talk about leadership, really understanding it, but I think you'll be able to explain it in a way that they will be able to understand it. Correct wording for hypothesis and rejecting the null. Yep, we will talk about that. Best statistical method, we'll talk about that. Best situations to use it. Yep, well, I think we'll get to all those. So I am going to thank you for those. I appreciate that. That really gives me a good context and that we're going in the right direction. And that's a lot to do with Doug. He planned this one. We've been splitting these up and he did a great job on this one. So what I'm going to do is we've got two examples here. And the first example, well, both examples actually, we're going to have two data sets. And they're going to be a fairly small data set in the world of data these days, because we've talked about big data. And we're going to have two samples of two shipments, and we're going to have a sample size of 25 in each one. We've got the means. We've calculated the means for you. And remember that you can fairly easily do hypothesis testing in Excel. You can do hypothesis testing, don't necessarily need like a mini tab or an SPSS or SAS or JUMP or those, because Excel helps us to do this pretty easily, and we'll see examples from Excel. So we're going to stick to Excel since we didn't know what kind of statistical software others had. But if you have questions, perhaps on Minitab, I could definitely help you afterwards as well. So we've got these two shipments, and they collected data, 25 samples, fairly small, and then they found that they had very similar standard deviations, about 0.320. So you could see that the first thing, we've collected data. We have decided that we're going to look at having a 95% confidence level or alpha of 0.05. And that's our type 1 error we're going to allow. And so we're going to be 95% confident. Now, if we had a very a process that we needed to be really super sure, and we didn't want a lot of error, we would up that confidence level to 99%, and then our alpha would be 0.01. So, and if we want the other way, if we've got a process that we don't have to be quite so confident, that's not a safety issue, it could be more of a service type of issue, then it might be at 0.1 or 90% confidence level. So we start then with identifying what our data is, how we're collecting that data, like Doug talked about, what our confidence interval is. We collect our data and we get averages or means. So we've got continuous data, and so we're going to use a hypothesis test that provides for us a test to compare continuous data, not discrete, continuous things that are measured. So in this case, there is some measure that says the mean is 5.4908 whatevers, and maybe it was inches or something, of our quality characteristic. We have some quality characteristic we've identified. And then the mean of our, oh, this would probably be time, sorry. So the shipment time is 5.4908 minutes. And for the other one, it's maybe 5.3580. Was that time based, Doug?
Yeah, that was time based.
Okay, thank you. And then our standard deviation was very similar. And we want to know, are those the same? So there's the difference between statistical significance and practical significance. And even though you can have something that is statistically significantly different, practically it's really the same. And so we'll kind of talk a little bit about those differences. So I'm going to go on to the next slide and show you this slide. And we have, again, our null hypothesis. So we start with the null hypothesis. And this is really what we want to potentially reject, right? Null hypothesis is if everything stayed the same. So if you think about process improvement, you tried to improve a process, you had a previous process and the shipment time was 5.4908. And then you did something, you had some intervention, you improved something, and the mean was reduced to 5.3580 minutes. Is that really going to be significant from a statistical perspective? And then is it meaningfully practically significant as well? So we took the 25 samples, we had our standard deviation of 0.320. Our t-test statistic, we decided we're going to do a t-test. So we could do a z-test. That's when you have sample sizes that are larger, usually over 30. But we have a smaller sample size of 25. This t-test, or the student t, and Doug put a little story in here I'll talk about. And this was based off of a fellow, and let me find his name, that was named William Seeley Gossett. And he was born in 1876 in Canterbury, Kent, England. And around 1895, he had worked in the Guinness Brewery in Dublin. What a nice place to work. And he started hiring Oxford and Cambridge grads to introduce scientific methods into beer production. And Gossett was hired in 1899. So in 1905, Carl Pearson at the University College in London provided Gossett with a half-hour crash course in almost all the statistical methods known at the time. Pretty amazing. And then Gossett started introducing these ideas into the methodology in the brewery. And what he found was usually his sample sizes were about 5. One, he probably had the concept of destructive testing, right? He didn't want to necessarily drink all the beer to taste it, to test it or to taste it. And so he usually had about 5 measurements. And it was difficult with a z-test to get accurate assessments on just a few measurements like that. So what he developed was a little bit of a different distribution, a normal distribution that was kind of flattened a bit, was a little bit wider, had a little bit more variance, a little bit more standard deviation. And so he wasn't allowed to use his name at Guinness. So he had to use a pseudonym to his test. He couldn't name it the Gossett test, which was unfortunate. So he did publish about it, but he did so under a pseudonym, and he called the test the student, or the student t-test is what this ended up being called. So I love that story. And it helps us to understand kind of where this came from, and, you know, only a little over 100 years ago. So that's pretty cool too. So what this does is it takes these values, and I'll show you the formula in a second, and you've identified your confidence interval, you've got your mean, your standard deviation that you calculate from your data, sample size of 25. And then we decide that we want to know if the time's a little bit less, the difference in time is less, or if it's greater. Now, sometimes, like when I was working in hospitals in the emergency department doing process improvement, I just wanted to know that maybe the triage time went down. I didn't really care whether it I just wanted to know that it was going down, that it was less than. I didn't really want to know whether it was up and down. It was I didn't really care if it was going to be way below the 0 time, because I didn't think it would get that close, because there's always going to be a little bit of time. So I cared whether it was a OneTail test. For this situation, we care about whether the new process is increasing time or decreasing time. And because if we try something new and the time goes up, we want to know that. If we try something new and the time goes down, we also want to know that. So the 95% confidence, the TwoTail test, the alpha value as 5%, or 1 minus the 95%, and then the critical value, and these are values that are calculated from the t distribution, that somewhat normal looking curve. And these are critical values that'll be a point on that distribution way out to the right, and anything greater in that 0.05 area or to the lower side is going to be significant. So anything to the right of the positive t critical value or the left of the minus t critical value, then we're going to reject. So go ahead, Doug. Okay, so now we have two different data sets, two shipments. We've got one mean. The first mean was the same. Now we have another shipment, and that was 5.379. So we have, again, the standard deviation's about the same. So we want to know, is that one significant? So go ahead, Doug.
I'm going to go back a minute and let them see the previous values.
Okay.
So 54908, 53580, and now it's 54908 and 53799. So again, a little bit different value. Here we go.
All right. So this is the setup. We've got our means, our two means, our number of samples, our standard deviation. This is our t statistic at the low, the minus value. This is the lower t critical value here. And so you could see, if you go back up to the other one, the critical value was, that wasn't the same. Did you go back? Okay.
This is the new data sets.
Okay, got it.
And the previous time where we rejected it, it was minus 2075.
Okay, so I didn't say it. Okay.
Yeah.
So I missed that, saying I've got an example using the p-value. I usually use the p-value. I always used to take out my statistics book, go to the table, and get that reject, that upper t critical value and the lower t critical value. However, in Excel or in a statistical package, it'll calculate the p-value, and it's easier to make the decision based on that. So this t statistic, if we've got the minus 2.064, here we've got the t statistic of minus 1.733. So it is not within the rejection region, right, Doug?
Yes, that's right.
We fail to reject. I'm sorry, the notes are saying something different. So we fail to reject. So I wish I could draw this on here, but I don't think I can draw on here. But so if we look at our distribution, and we've got, I think, an example next, we've got the rejection is minus 2.064 value. So you think negative number line, minus 2.064, but the minus 1.733 is within the bulk of the data in the middle, not out in one of the tails. So we fail to reject because we would only reject if it's way out past the rejection region or just past the rejection region. So let's go to the next one. Our T statistic, whoops, I'm sorry, that was the second one. Go back to the very first one so it shows we did reject the first one. Okay, this one was greater. It was in the rejection region. It was to the left of the minus 2.064. So we do reject. We say that the 5.4908 mean is different from the 5.3580. Our null hypothesis, no difference between the means are the same. So we reject the null hypothesis. So we conclude that there is a difference. There's something happening that's causing this difference. Go ahead into the second example. Now for this one, the difference between 5.4908 and 5.3799 that we fail to reject, there's not a statistical difference between them. There's a numerical difference, but there's not enough of a difference with the sample size, with our rejection region, with our standard deviation to reject the data. So there's not yet a difference that we're seeing in the processes that cause these means.
Okay.
And then, okay. So we want to talk a little bit about the student T distribution. Again, this is recommended for tests under a sample size of 30. There is a reference that Doug gives, the Barcelou and Smith. There's lots of different references in statistical books that will show you the formula for the student T distribution. Go on, Doug. Okay. There are a lot of other statistical tests, and then there are depending upon what data you have. So these are the main ones. When I teach this material, you can see that if your test statistic, your quality characteristic is continuous data and you get a mean, an average, then if you have two processes that you're comparing, you have a t-test, and you can select that you have a two sample t, either variance unknown, assuming equal variances, or variance unknown and you don't assume equal variances. So, and this is going back to your population. You don't really have enough data on your population to know whether your variance is known and it can be assumed equal. So there's just kind of different check marks on your statistical package that you can select that differentiates between those, but it's still the student T distribution. If you have, you're going to say something, Doug?
Yeah. In this class, this presentation, we chose what might be a very common situation. You're looking for differences in means, averages, and you only have a few samples. And the standard deviations are really about the same, equal standard deviation. So that's why we chose that. But there's all these others you could use. Go on, Teddy.
You could also compare, if you're comparing subjects that are doing a before and after comparison, you're giving a medication to the subject and you're seeing if there was a difference in how they reacted to the medication. That would be a paired t-test, paired by subject. If you have a proportion, like a percent, like maybe percent of people who pass the test, then you can do a two proportion test. If you're testing variance, you'd use your F-test. And then if you're testing survey questions, you would use chi-square. So these are for survey questions, count data. Okay, so this is the picture, kind of wanted to try to show everything on one slide. So the TwoTail critical region, so we've got this minus 2.064. Remember that the first one was minus 1.76. It was within the white set part, so we failed to reject. It did not get out into the tail. It's very unlikely that anything changed between those two distributions. Our other test was minus 2 point something that was greater than this minus 2.064. That probability that something changed is very slim if it gets out into that area. So, or the probability would be slim that it got into that area and that something didn't change. So something must have happened in our processes to cause that minus 2.075 to get out there. This is the formula for the T statistic, taking the difference between the first mean minus the second, dividing by the standard deviation. We used a pooled standard deviation across the two samples, and dividing by the square root of n. These were our values that we put into there. This is how we got our 2.075. Because we're interested in it being out to the left, we have it as a minus value since it's a left one-tail test. Since we're trying to test if it's less. Then using that function in Excel, the t.dist.2t, we have that x value of 2.05, which was this difference. This is a different test right there, 2.075. Or maybe that should be 7.5, I'm not sure. Degrees of freedom 24, and a p-value is ends up being 0.0489. So I usually use, so instead of going to my tables and getting these critical values, I don't get my critical values. I just calculate the p-value out of the formula here and the function in Excel. And the decision I use is if my p-value, if p is low, HO must go. So I always can easily say, okay, if my p-value is less than my significance level of 0.05, then I reject my HO. So in this case, for this 2.075, and this should be a 2.075 here, that this gives me a p-value that makes this in the rejection region, in the red, and so it's less than 0.05, so I reject. And the next one. And this is the second test, was the value of the minus 1.733. It's in the white, it's not in the red, so we fail to reject. So if you go to the next one. So here's my calculating the 1.733, put that in as the X, put my degrees of freedom as 24. This gives a p-value of 0.0959. It is greater than 0.05, so I fail to reject. P is not low, so I fail to reject the null hypothesis. Okay, so a little bit about the errors. The type 1 error is when we reject the null hypothesis when in fact it is true. There's a very slim chance of doing it, but there still is. And that's what the 0.05 versus the 0.10 and 0.01 provides for us. If we want it to be very small, then we go with the 99% confidence or p-value of 0.01. The type 2 are when we fail to reject the null hypothesis when we should have. The data didn't show us that in fact something changed what it really had. Our samples could have been non-random or non-representative in some way, so the conclusions were an error. Okay. So just a few common mistakes. The first thing is, one of the first things you want to do is, what are you testing? What quality characteristic are you testing? You want to identify that. So that's going to guide you into whether it's a continuous test, such as a z-test or a t-test. And you want to define exactly your null hypothesis. There is no difference between the means in this case, or there is a difference, significant difference. You want to identify the alpha value. And again, usually the more serious or hazardous or safety oriented your characteristic and your process is, you want to go to a smaller alpha or a higher confidence level to 99% or 0.01. Ignoring the effect size, the data snooping. Explain these a little bit here. The effect size is that you are looking at the determining statistical significance, but you might not assess the importance of an observed effect. And this is kind of the difference of practical significance versus statistical significance. The data snooping or multiple comparisons, you're not really thinking through identifying all these values, and you'll be making the wrong assumptions there. Neglecting assumptions. What are your assumptions? What quality characteristic are you using? What is your null and alternative hypotheses? What is your significance level? The misinterpreting the p-value, excuse me, not really thinking about if my p-value is low, if p is low, HO must go, make the opposite decision. We talked about confusing statistical and practical significance. You can have a statistical significance without, and then go to your boss and say, it's statistically significant difference. And they go, yeah, but is it costing more? Is it bothering the customer? Is it, the practical side of it? It might not be practically significant. The, performing other tests where you're not carefully planning, overlooking sample size, and really failing to reject the null hypothesis does not make it true. Okay, so you've got to kind of think about what is it that rejecting is saying is really doing. The non-significance sorry, could be due to various factors. And so you really have to make sure you're sample size, looking at the variables that impact.
Sandy, your audio is cutting in and out, I think.
Okay. All right, next. Okay. So we really had time to just give you a little snippet of some of the decisions that you want to make and the assumptions that you want to set up, and looking at the different tests and whether it's a OneTail or a TwoTail and so forth. And just overall the importance of actually doing this. I remember one time I was mentoring a student in that was doing process improvement in a hospital, and she had a very low sample size. And then her variance, her standard deviation was very large. And even though practically looking at it, it seemed like the times were very different, because of the small sample size and the variability, it wasn't statistically significant. So she just had to wait it out, collect more data, and work additionally on the process to improve it. So sometimes, people, especially that don't know statistics, will just look at the data and go, yeah, we improved, but you really have to run the tests. So if you take one takeaway from this, you really have to run the tests, set them up properly, and kind of know what you're trying to show when you're using hypothesis testing. So the most important thing is that you stop and you actually do it, and you don't just assume because you have very large numerical differences that equates to statistical difference. So, right, I think that was it.
Yep. These were the sources and materials that I used in preparing the slides. Barcelow and Smith. Okay, those are Minitab guys. Okay, so that tells you where that came from. I indeed used Sandy's chapter from the CQPA handbook, which of course is something we're using in all of these presentations in this series. I used the cartoon guide to statistics. Well, it's not a cartoon. it just uses pictures to illustrate things. And I also did reference Duran's Quality Handbook, the 7th edition in this one. So it's a lot of good material out there for though.
Oh, Doug, I just realized I knew something was driving me nuts when I was talking about this. I've got to fix slide 28. I've got just the wrong picture on it. So I had the right information. Slide 28, the picture was wrong. This should be the 1.733 picture.
Is
I
that this
think
one
that-
here?
That it's the next one, I think, or maybe it's the next one. Yeah, it's this one.
Oh, yeah, I get it. So this says
yeah.
1.733, and this one should say 1.733
Yeah.
also. The purple
didn't-
down here at the bottom, right?
Yeah, I didn't, yeah. We just have to fix that, so.
Okay,
We'll fix that. And speaking of which, if you do want the presentation, Doug has proven, I think we ran a hypothesis test, I'm not sure, but I think there was a statistically significant difference that he actually gets these slides out to people quicker. So please send him the request for the slides.
Okay, we'll fix that typo on that slide.
Yeah.
Okay, so again, this course, the series comes from Sandy's book that you're looking at there. We want to tell people what this certification is for. It's kind of like a certified quality engineer light, but it's also something I think that is ideal for people who do not work in a manufacturing environment, but work in a transactional or office environment. It's probably geared more for them. Would you agree, Sandy?
Yes, definitely.
Okay. Okay, so here's our contact information. You may, jot this down, or you'll get this in an email after the presentation. And yes, you'll get
Right.
the certification units. So, Shobha?
Yeah, thank you so much, Doug and Sandy. So what we'll do is we'll begin with the questions. We'll leave the slide on for folks to just take a picture of your contact while I take up the questions. I think you've done a very good job taking up the questions in between, but let me just go through what I have collected. So can you test the hypothesis at different scenarios? One scenario says it's null, and then the other says it's a little significant.
Sandy? What do you think?
I'm not sure whether that's the difference between practical and statistical. What the statistical significance gives you is, it's kind of like Joe Gannon with Dragnet. It's just the facts. It's gonna tell you definitively, knowing your significance level, whether your process has changed. But the practical significance is that change enough for it to make a difference in your business, is kind of the way I think of that. So you can get all excited about it's statistically significantly different, but so what? It really has to make a difference in your organization. The customers have to be happier. The cost must have gone down. Something practically should be different as well. So just know, we get all geeky and excited about the statistics and showing that something's different, but it might not be practically significant.
Okay, the next question is, can you discuss some of the other statistical methods that can be used aside from the p-value and t-statistics, and what different ways they show the data? I frequently use z-score, f-ratios, and confidence intervals for means in my analysis of data when I'm not sure what might show up statistically significant. For instance, because they all show different things about the population depending on which ways you're comparing your data.
So I think if you're using the t statistic and comparing it to your table value, your critical value, versus the p-value and the confidence interval ways, then it's all saying kind of the same thing. And you should get the same decision, the same results. When you're talking about some of the other ways to do it, when you're saying Z versus T, those are different tests those are based on what quality characteristic you have and how much data you have. So the foundational three ways kind of that are traditionally the avenues to make a decision are the T statistic and critical value, the P value, or the confidence interval. Doing all three of those, you should still be making the same decision.
Okay, let's go on to the next one. In order to the test be valid, do the standard deviations need to be about the same?
They should be. That's one of there was in the slide, Doug had the three basic assumptions of doing the statistical tests, that there's independence of the data, that they're not somehow correlated to each other, that they're normally distributed, and you can test for normal, whether the distributions are normal, and then that the variances are approximately the same, and you can do the F statistic or the F test, tests of variances to test for that. So we haven't gone into it as much, but definitely when you state your assumptions, then you're going to want to run a normality test and run a variance test to know whether you're able to use the Z test or the T test, because those do rely on normality of your data. If it's not far from normality, usually they say it's probably okay, but if it's vastly different, you're going to have to use like a median test or some other kind of non-parametric test, not assuming a distribution.
There were two questions related to the examples you showed. So one was that why is the upper and lower T critical value 2.064 on the second example?
Well, the T statistic stays the same. I'm sorry, the critical value, the T critical value stays the same as long as your confidence level stays the same and your sample size, degrees of freedom stays the same. You're just comparing your T statistic that you calculate, which I showed the formula of the x1 minus x2 over S over square root of n. Does that make sense?
And then another question was, good example of two shipment data. The question is, are data normally distributed?
Yes, so Doug would have had to check that.
Yes, this data was normally distributed. And as Sandy said, it can be very close to normal and still work. But you do need to run a normality test on the data you're getting if you don't know that it's a normal distribution. Many processes are normally distributed. In general, if you have a large number of factors that influence a result, it will very often become normal. Things like how fast you walk, how tall are people in a room. Those tend to be normally distributed because there's many factors behind them.
Okay, we'll take the final question. What is the standard confidence level that is normally used in the automotive industries and in the military industries?
Oh, you mean I guess the confidence level?
Yeah, what is the standard confidence level that is normally used in these two industries?
I'm not for sure. I always hear 95%, but again, if it's for keeping people flying in a plane and their safety, it's a safety oriented quality characteristic, I would say 99% safer.
There isn't a standard. It depends on your management. It depends on the situation. Critical items are going to be, want a higher number. Not so critical would be lower. And that's a decision made by the management.
Okay, so we can roll on to the next slide. George is finishing up the program. So these are our upcoming webinars. We have on August 2, A Future of Work, Adapt or Become Outpaced by Dr. Deli Ola. On August 16, We have ASQ and QM division joint webinar, which is a continuous development of LSS practitioner, meeting the business needs through consulting. And then on September 6th, we have how supply chains can be more resilient by practicing lean. And then on September 20th, we have leadership for organizational excellence. So we have a good lineup coming up within the next 2 months. Please tune in. Next slide, please. So if you have not joined ASQ, please consider joining it. It does have a lot of good information and very practical ways of solving problems. So do check it out when you have a minute. Next one. So looking into my ASQ and then finding quality management division, if you go under communities and then if you scroll down, you'll find, and if you use this QR code, it does lead you to our quality management division. Again, lots of information in there for you to take advantage of. Next slide. So that ends it for today. I want to thank you all for coming and attending it. And I really want to thank Sandy and Doug for the wonderful presentation. Thank you all and have a good night.
Good night, everyone. Thanks for joining.
Yeah. Good night.